Okay, so these are some past paper questions that deal with work done, energy, and vehicle design. If you go into your board, you'll find them in this bottom right-hand corner, and it's these questions here. Okay, so got a paper copy ready, and these questions refer to the following part of your specification. You move back across here to find your specification, which is here. So they take their inspiration from a number of bits of the syllabus, but specifically the last two here. Okay, so how energy efficiency of vehicles can be improved, and the principles of force and motion to the analysis of safety features of cars. Okay, so that's where most of these questions take their inspiration from. So, question number 1, also known as question number 6. Cars are tested so that the manufacturers know what happens to the passengers during a collision. In one such test, a car of mass 1,500 kilograms traveling with an energy of 127,500 joules strikes a solid barrier and stops. The force applied to the car by the barrier is 500,000 newtons. So name the energy that the car possesses due to its motion. Okay, so anything that's moving is said to have kinetic energy. State the work done by the barrier to stop the car. Okay, so work done is measured in joules, and at the moment, the only sort of information we've got there in joules is this figure here. So if the car is traveling with that level of energy, when it stops, the barrier must do that much energy in order to stop it. Okay, so that's 127,500. And then it says use the equation, distance is work over force, to calculate the distance over which the force acts. Okay, so again, the only information we've got from the question that might help us here is the work done, which we've already established is that number there, and the force of the barrier to stop the vehicle, which is this number here. Okay, so right there, 127,500 joules, that's the work done, divided by 500,000 newtons, which is the force required to stop the vehicle. And if we put that through a calculator, we will get 127,500 divided by 500,000 is 0.255 meters, or 25.5 centimeters. Okay, so it stops in a very, very short space of very short space, rather. It's only 25 centimeters, so the length of a ruler. So if you're sat in that car, a lot of that energy might be transferred to you. Okay, so state one feature of cars that is designed to keep the drivers safer in a head-on collision. Or perhaps the most obvious answer there might be a seatbelt. You might also mention airbags. And you could also mention the crumple zone, which is the area, the bonnet of the car that is designed to deliberately collapse in a crash to try and remove as much energy as possible so it doesn't get transferred straight to the passengers. And then explain how this safety feature keeps the driver safe. Okay, so for the seat belt, it stops them carrying on traveling, so it stops further travel through the windscreen. So it is quite brutal in doing that. Airbags, similar sort of thing. They act as a cushion against the impact against the dashboard. And then the crumple zone, as I mentioned before, removes the energy of the impact. Those are three features that reduce the chances of injury during a collision. Okay. Okay, move on to the next question. Bit of a fairy tale, it would seem. It says, as part of a charity event, a woman jumps from a tall tower and she lands safely on a large airbag that is beneath. We're told in the diagram that she's experienced air resistance and her weight, which is a value of 550 newtons, and she's going to hit this airbag. On Earth, an object of 1 kilogram has a weight of 10 newtons. Calculate the mass of the woman. Okay, so if she's got a weight of 550 newtons, okay, if we divide that by 10 newtons given to us in the question, and that gives us a mass of 55 kilograms. Okay, so that would be 55 kilograms there. So the units of this are 10 newtons per kilogram on Earth, and therefore the newtons would cancel, and the per kilogram becomes kilograms because you divide it by it. Okay, so that's first part of the question. Second part says the woman hits the airbag with 5.6 kilojoules of kinetic energy. Just take a note of that, kilojoules. The airbag stops at a distance of 2.8 meters. Convert 5.6 kilojoules into joules. Okay, so kilo means 1,000. So basically that's 5,600 joules of energy. Okay, so 5,600. Use the equation mean force is work done divided by the distance. Okay, to calculate the mean force bringing the woman to rest. So the work done, as we've seen in a previous question, is measured in joules. It's energy, and we've got the value for energy here, and the distance quoted in the question is 2.8 meters. So 5,600 joules of energy divided by 2.8 meters. Again, if we employ our friendly neighborhood calculator, so 5,600 divided by 2.8 is 2,000 newtons. Okay, so that's 2,000 newtons acting on her to slow her down. It is suggested that it would be safer if the airbag was filled with water. The distance to stop the same woman falling from the same tower would be 0.8 meters instead of 2.8 meters. Without further calculation, explain whether you agree with this suggestion. Okay, so just from an experience point of view, if you hit water from a height, you probably know it hurts if you've done a belly flop, but also the fact that it stops her in a much shorter distance, and you still have the same energy involved, and therefore the same sort of the same energy, it's gonna hurt basically. So no, the same amount of energy be dispersed into the woman but a much shorter distance. Basically, not a good idea to hit a bag of water when the alternative is a bag of air. Okay, and then final part of this question. So a car is traveling at 10 meters per second along a flat road. A driving force of 50,000 Newton acts on the car for a distance of 20 meters, causing it to accelerate. Use an equation on page 2 to calculate the work done by the 50,000 Newton force. Okay, so we don't have a page 2, but we do have access to our syllabus. Okay, so we're looking for work done. The work done using the force we're given here, and we're also told a distance. Okay, so the force done, so the work done is force times distance, and our force in this instance is 50,000 newtons. Now a distance is 20 meters. Here we don't need to worry about changing units because those are both in appropriate units. So 50,000 times 20 is absolutely right. So 20 times 50, 1, 2, 3. Yeah, it says 50,000 is a million joules. Okay, so that's a million joules. The car gains 600,000 joules of kinetic energy as it accelerates. Calculate how much energy is transferred in other ways. So this is the energy transferred to the vehicle to accelerate it. However, is not all transferred into kinetic energy. Some of it will be transferred into other forms of energy, such as sound and heat. And we're asked here to calculate how much that is. So 1 million take away 600,000 is going to equal 400,000. Okay, so 400,000 joules of energy is transferred into heat, sound, and other wasted energy, because the whole point of a car, or the engine of a car, is to try and drive it forward, and an awful lot of the energy that's supposed to do that is wasted. Okay, so state 2 ways that the design of the car could be changed to improve its efficiency. We could look at the shape of the car. We could streamline the car to ensure that it's experience the least wind resistance possible, and we could make it lighter. If we made the vehicle lighter, that would help, and then we could improve efficiency of the engine. So as much of the energy and the fuel is transferred into kinetic energy as possible. Those would be ways in which we could try and reduce this figure here, which is 40% of the available energy. Okay.